today. 7.8 on improper integrals. And it consists of two types of improper integrals. The first one is two types. The first type is type 1 is the one infinite interval. Infinite interval. So it goes to infinity, or it comes from negative infinity, or even negative infinity to infinity type. Okay, basically the idea is, oh, let me do type 2. Type 2 is the one involving infinity, discontinuous integral. Discontinuous integral. To be more precise, it's called discontinuous with discontinuous with infinity. Now, the idea will be as the following for type 1. Suppose we have integral from a to infinity of a function fx dx. Now, this integral actually represent, we can say this integral actually represent the area under the curve. If the function is non-negative, the area under the curve from a to infinity. From a to infinity. Now, to compute that, we will compute the integral from a to t. So we use a dummy variable t. We will integrate up to t. And then we push this t goes to infinity. Okay? That will be limit t goes to infinity after we get that integral. That's the idea. So the idea is actually quite simple. The idea is actually quite simple. It's the later on we need to compute the limit together with the integral. That's the one make it more complicated. So let's say, for example, we do problems from our book. Question number 6. Question number 6. Integral from 0 to infinity of 1 over the 4th root of 1 plus x dx. Now then we will write this as a limit first. Limit integral from 0 to t, and later on we push that t goes to infinity. Okay, of 1 over 4th root of 1 plus x dx. Okay, and then from there we compute that as usual. Okay, but please be strict with your notation. You are in calculus 2. You are in calculus 2. when I already grade like 3 pages of your test, and a lot of you were not that strict with your notation. No, you have to be strict with your notation. You are in calculus 2 already. Okay, and in fact, because you are not strict with your notation, I caught two students cheating from each other. That's kind of sad, huh? Okay, because of your notation, you kind of like, I found you were cheating because of your wrong notations. And the probability that two of you use the same wrong notation multiple times on the same page tells me a lot about what both of you doing. So if two of you listen to this, I strongly suggest you to drop the class. Okay, if test 1 you already start cheating, trust me, you have no chance for this class. Well, anyway, come back here. How do I integrate this? Oh, well, then I use substitution, right? U equals to 1 plus x. So du equals to dx. So limit t goes to infinity, integral. This becomes 1. This becomes t plus 1. Okay, and then this is u to the power of negative 1/4, right? du. And integrate that, we get 3, oh, sorry, limit first. I need to write the limit first. Limit t goes to infinity of 3/4 or 4/3, should be 4/3. 4/3 u to the power of 3/4 from 1 to t plus 1. That is limit t goes to infinity will that go to infinity? That's 4/3 t plus 1 to the power of 3/4 minus 1 to the power of 3/4. That's 4/3 limit t goes to infinity of t plus 1 to the power of 3/4 minus 4/3. But this will go to infinity, right? So this integral is divergent. Integral from 0 to infinity of 1/4 root of 1 plus x dx is divergent because it goes to infinity, or if it goes to negative infinity, or does not exist, if the limit does not exist. Another example, number 8. Integral from 1 to infinity of 1/2x plus 1 cube dx. If my u is 2x plus 1, oh, you know what? I need to do the limit first. See, I myself want to rush. So be very careful with that problem, okay? Set it up correctly first. Limit t goes to infinity, integral from 1 to t, 1/2x plus 1 cube dx. And then I do substitution. U equals to 2 dx. Because of that substitution, of course, the limit of integration should also change. this becomes integral from 3 up to 2t plus 1 u to the negative 3 du over 2. That is 1/2 limit t goes to infinity of negative 1/2 u to the negative 2 from 3 to 2t plus 1. That's negative 1/4 limit t goes to infinity for 1 over 2t plus 1 squared minus 1 over 3 squared. That's negative 1/4 limit t goes to infinity of 1 over. You know what? I can just plug in the t right now. Why I work so hard? So that will be 1/4 parentheses 0 minus 1/9. Right? That's positive 1 over 36. So it is convergent and convergent to 1 over 36. Number 10. I hope you are not bored with me, because it's more about applying that concept. Number 10, integral. What happens if we have integral from negative infinity to 0 of 2 to the r dr. So we set the left-hand limit of integration to be t, and later on we push this t to very far to the left to negative infinity. No substitution needed. This is limit t goes to negative infinity of 2 to the r over natural log of 2. I hope you remember that, right? From t to 0. So this will be limit t goes to negative infinity of 2 to the 0, which is 1, minus 2 to the t. Oh, I almost forget the constant over ln 2. Okay, but 2 to the negative infinity is 0. So this is 1 minus 0 over ln 2. The issue arises when let's say we have from negative infinity to infinity, like number 22. Finite number, I think. Hold on. What do you mean by finite number? Sorry. From Andre. He asked what is convergent. Oh, convergent. Yeah, convergent if it is up to a certain number. Yeah, not going to infinity or not going to does not exist. The limit not going to does not exist. Okay. Number 22. number 22, integral from negative infinity to infinity of x cubed e to the negative x to the fourth dx. Now the thing is, we go from negative infinity to infinity, right? Now the way we're supposed to do this, okay, I actually don't like this kind of interruption. I'm working on 7.8. You asked me about 7.6, 7.7. I skipped that for a reason. I will tell you later on. But since you asked me now, then I will go back to 7.7 later. I don't know how much later. How about 7.6? That's just using table. I don't do that. Okay, I will skip that completely. And trust me, the problems I give you still at that level. So if you want, you can try working on those problems anyway. Okay, but for 7.7, I plan to go back. I just don't know when will I go back, because from my experience, if I go back to 7.7, then I may not have enough time to finish chapter 12 later on. And 7.7 will be done a lot easier if you know computer. Okay, I wonder if you use, what's that? I will explain it using Excel later on, because everybody have Excel, right? But I may use, what's that? The programming language. I forgot. More recent one. Python. I may use Python to teach 7.7. I will see. I will see. I can use Python, and then you wonder what is Python, Thomas, right? Then I will just use Excel. But when I use Excel, somebody may ask me, Thomas, can we use Python? Okay, and then once I use Python and Excel, somebody ask me, Thomas, can I use C++? It's just like never end. Okay, so I will use something, and I will use Excel very likely. Okay, Excel will be able to provide us a better view without less of detail. Now let me come back to this then. What happens if we have negative infinity to infinity? What you can do is you choose one number in between. Any constant in between will do, but preferably, of course, 0. Okay, you can use 1. Okay, and then you choose two numbers on the left and the right of that. Let me use, let's say, I don't want to use s because it looks like 5. I use s anyway. Okay, but my s looks like that. And then t. Now later on, I will push my s goes to negative infinity, and my t goes to positive infinity. That's the plan. Okay, so I will break this integral into two parts. Integral from negative infinity to 0 of x cubed e to the negative x to the fourth dx, plus integral from 0 to infinity of x cubed e to the negative x to the fourth dx. Again, so I break this interval from negative infinity to infinity somewhere in the middle, 0. Can I use 1, Thomas, instead? Yes, you can. Can I use 2? Yes, you can. I just wonder why you like ugly numbers when you can choose nice numbers. Okay, the only time I would choose ugly girl is when I have more benefit by choosing that girl. Okay, let's say that person have a brain. That person make a very good money so that I don't need to work, right? Okay, of course, that's a joke. But try to make sense of that. If you have a choice, why you want to choose a hard one? Can I choose pi, Thomas? Go for it. Okay, now then this is limit. On the one on the left, I will use s going to negative infinity. As from integral from s to 0. Make sure it doesn't look like 5 though. Okay, x cubed e to the negative x to the fourth dx plus limit t goes to infinity, integral from 0 to t, x cubed e to the negative x to the fourth dx. And then I do substitution, u equals to x to the fourth, so du is 4x cubed dx. Okay, so I happen to be able to use the same substitution for both. Okay, this will be 0, this becomes s to the fourth, e to the negative u du over 4 plus limit t goes to infinity, integral from 0 to t to the fourth, e to the negative u du of 4. My x cubed dx, x cubed dx is this x cubed dx, right? Okay, now then this is 1/4 limit s goes to negative infinity, and the integral of e to the negative u du is negative e to the negative u from s to the fourth up to 0 plus limit, don't forget the 1/4 times 1/4 limit t goes to infinity, negative e to the negative u from 0 to t to the fourth. This will be 1/4 limit s going to negative infinity, negative 1 plus e to the negative s to the fourth. Correct? Plus 1/4 limit t goes to infinity of negative e to the negative t to the fourth plus 1. But that's equals to 1/4 times negative 1, right? And then plus 1/4 times 1. That's equals to 0. But be very careful with the following argument. Let me write this down. Wrong way to do number 22. It's actually a good idea. The following way is actually a good idea. It just happened that when we do negative infinity to infinity, this is not the correct way. Okay, somebody argue this way, in this integral from negative infinity to infinity of x cubed e to the negative x to the fourth dx. Somebody argue this way. Note that fx, the integrand fx x cubed e to the negative x to the fourth is an odd function. That is f negative x is equals to negative x cubed e to the negative of negative x to the fourth, which is negative x cubed e to the negative x to the fourth, which is negative fx. And we know it's an odd, if a function is odd on a symmetric interval, then the integral is 0. So integral from negative infinity to infinity of x cubed e to the negative x to the fourth dx. That person say, let me use t as my limit of integral. Okay, and I will go from negative t to t of x cubed e to the negative x to the fourth dx. But because it is an odd integrand, then this integral will be 0. I wonder if you remember that. Like if you remember, this is just a scratch word. Okay, if you remember, let's say I have integral from negative 3 to 3 of x to the fifth dx. This is equals to 0. That's equals to 0. Why? This function is an odd function, and the limit of integration is symmetric around 0. You can try to integrate that. You will get 0. Okay, and in fact, it doesn't have to be 3. You can change that to 300 and still to get the same zeros. It applies to any t. Okay, so if that person, if you try to argue this way, if you try to argue this problem this way, it is true that this guy is 0. It is true. Okay, but the problem is actually here. Our issue is here, from here to here. What's the problem? The thing is, when you go to negative and positive infinity, the way they approach negative and positive infinity has to be independent to each other. Okay, so this is t. The way you do it, this is t and this is negative t. Right? And they go to positive and negative infinity with the same speed. But that's not how we can argue the case. Okay, that's not how we can argue the case because of the following. Because of the following. For example, the same argument doesn't work if we use this. So it seems like the answer is 0, which happens to be the same with our answer. Okay, but this is a wrong way because you assume the t goes to infinity the same rate to the left and to the right. Now, the thing is, you will see this doesn't work for, let's say I have x cubed dx. It doesn't work. It doesn't work. It just works if you do it this way, but it doesn't work systematically. Right? You say, oh, you know what? This is limit x, t goes to infinity, integral from negative infinity to infinity, x cubed d, I'm sorry, this is t here, negative t here, dx, and because that's an odd function, as limit t goes to infinity of 0, then it is 0. That's if you do it that way though. But imagine if I do it this way. Limit t goes to infinity, okay? But the one here, I make it 2t, and this is negative t. Yeah, both of them goes to infinity, by the way. I just make it that you go to positive infinity twice faster. I use 2t here, and I use t here. So you see, the one on the right-hand side goes to infinity faster, but both of them goes to infinity. You cannot deny that both of them goes to infinity and negative infinity. But the thing is, this is not zero. That's not zero. Okay. In other words, they happen to work only if you choose this kind of rate. Okay. That's why it is incorrect to argue this way. It's incorrect to argue this way. The correct way to argue is that you separate them. You have to separate them. Okay. You have to separate them into two integrals. Okay. And each one of them convergent. If any one of them divergent, then it's not convergent. Okay, you need to cut somewhere in between. Okay, so this is my scratch work here, just to give you an illustration that you have to cut somewhere in between. You cannot use symmetry because your choice of symmetry may not be the correct choice of symmetry. Okay, this is a good, I hope you can see this as a good illustration here. Okay, and this will go to positive infinity. This will go to positive infinity if you do it this way. On the other hand, if I say limit t goes to infinity of integral from negative 2t to t of x cubed dx, this is negative infinity. So which one is the correct one? Is this integral 0 or infinity or negative infinity? Then does not exist, right? Okay, that's because the result you get depends on the choice of how your t goes to infinity. So no, that's not supposed to be. Okay, they supposed to go to positive and negative infinity at independent rate, and that can be only done by using this approach. Okay. I don't see other type of question like that here. Let me ask you to do one problem. I hope this problem is not too hard for you. Number 14. Well, no, number 16. Why not? Number 16. Integral from negative infinity to infinity of cosine pi t dt. Can you do that? How many minutes? Maybe 5 minutes for this question? Okay, 5 minutes. What do you get? Cosine pi t dt. I want to claim that one of them does not exist. The limit does not exist. So let's do it this way first. Limit s goes to negative infinity, integral from s to 0 cosine pi t dt plus limit t goes to infinity from 0 to t. Oh no, I cannot use t because that's in t already. Let me use y then. Y goes to infinity from 0 to y. Integral from 0 to y of cosine pi t dt. Note. Limit y goes to infinity. So I set aside, I deal with part of that integral. Instead of both integrals at once, I deal with one of them. But you need to write kind of like a separate. You don't have to use the word node, but you need to kind of like do a certain notation to say that you are not continuing from what we had above. Okay, now this is equals to limit y goes to infinity of 1 over pi sine pi t from 0 to y, which is 1 over pi limit y goes to infinity of sine pi y minus sine 0, which is 0. Now the thing is, this does not exist. The limit does not exist. So this integral from negative infinity to infinity of cosine pi t dt, because part of that does not exist, then the whole thing also does not exist. Yes, then it is divergent. That's why we call that not exist. If it is convergent, then it goes to a certain number. And if it doesn't go to a certain number, then we call it divergent. Okay? Integral negative infinity to infinity cosine pi t dt is divergent. Somebody asks, why does not exist? Y does not exist. Then plug in y equals infinity. So what happened to that if y is infinity? Does it give you a specific number? No, right? Okay, so the behavior of sine why does not exist. It's actually the same question with this limit x going to infinity of sine x. What is this equal to? That does not exist, right? It does not exist. It's not x going to 0. When x going to 0, then sine x will be 0. Okay, but when x goes to infinity, you know that sine x is oscillating from -1 to 1. It's bounded, but not convergent to a certain number. Okay, the second type 2. Type 2 is the integral that goes to, that contain interval that goes to infinity. Type 2 is continuous. Integrals. So the idea is the following. Suppose I have integrand, let fx is discontinuous. In fact, it's discontinuous to infinity you have a vertical asymptote, especially when it has vertical asymptote. But as long as it is discontinuous, we will do the following. Let's say fx is discontinuous at x equals to a. So that's x equals to a. And then I want to find the integral from a, let's say from a to b. Okay. Now the idea will be, I will take the integral from t to b. I get the area here first, and then I push my t to a. But I will push my t to a, t will approach a from the right-hand side in that case. Suppose the discontinuity is on the right-hand side, the right-hand limit of the integral. Suppose the discontinuity is like this. Then what we will do is I will do integral from a to t. And then I push that t approaching b from the left-hand side. Okay, that's the plan. That's the plan. Now, what happens if it has discontinuity in between? Let's say I have this discontinuity at c here, at x equals to c, and the curve looks like this. So it escapes to infinity. Okay, and then you want to integrate, let's say, from a to b. So yes, you will break the integral. So the integral from a to b, later on you will break it into integral from a to c plus integral from c to b. And then that's equals to limit s to c from the left-hand side of integral a to s plus limit t going to c from the right-hand side from t to b. Okay, so again, basically this integral from a to b, because we have this continuity at c, we will break it into integral from a to c plus the integral from c to b. Okay, now then the one from a to c will be done from a to t. And then you push this t going to c from the left-hand side. While the one on the right-hand side here, you will integrate, let's say, from s to b, and then you push that s go approaching c from the right-hand side. So that's how we avoid the infinity. Okay, that's how we avoid the infinity. We deal with that infinity later. That's the plan. That's the plan. Let's work on this. Suppose, for example, we do number which one's good? Number 28. Integral from 2 to 3 of dx over square root of 3 minus x. You see, it becomes undefined when x equals to 3. Right? It becomes undefined when x equals to 3. You can try to visualize what happens with the interval. So the interval is from 2 to 3. Right, from 2 to 3. But this continuity here, right? At 2 is okay. At 2 is okay. This continuity at 3. So what you will do is you pick from 2 to 3 to t, and then you push it to 3. That's limit t goes to 3 from the left hand side. Integral from 2 to t of dx over square root of 3 minus x. Okay, and then from there you integrate as usual. U equals to 3 minus x, so du is negative dx. T goes to 3 from the left hand side. Integral from 1 to 3 minus t of negative du over u to the power of 1/2. That's limit t goes to 3 from the left hand side. Integral from 1 to, you know what, let me change the order of integration. Limit of integration, 3 minus t up to 1 to absorb the negative, and then u to the negative 1/2 du. This is limit t goes to 3 from negative side, from the left hand side. Of 2 times u to the power of 1/2 from 3 minus t to 1. This is equals to 2 times 1 minus limit t goes to 3 from the left hand side, smaller than 3. Okay, of 3 minus t to the power of 1/2. This will be 2 times 1 minus 0. Okay, so it is convergent to 2. Now, nothing really special about what we do after this, though. Nothing really special about this. To be honest with you, we have learned everything from here and on. This section is really just teach us this thing. That's what that section is about. This section is about. How to integrate that, that's something later. I mean, we learned that before. Okay? So what we learn in this section is basically how to break it up and use limit to compute that. Now, some of you may question, Thomas, can I just use infinity right away without using the limit thingy? So far, I get the same answers. I agree with you, but the thing is, that's actually when you don't know when you get different answer if you don't do it appropriately. Okay, if you don't do that appropriately, you will not know if you get the right answer or not. Let's see number 30. For the limit, do we need to use different variables like s and y? Can you use both s? No, you cannot use both s. It will be confusing because one s for one type. If both of them, for example here, if you use this to be t and this one also t, then later on your t may cancel while they are not supposed to cancel. You see? Setting both of them to be t, you are saying that both of them approach c at the same rate, while they're supposed to be independently approaching. Okay? So the answer is no, you cannot use therefore you cannot use the same variable. Okay, number 30, we have integral from 6 to 8 of 4 over x minus 6 cubed dx. It is undefined at 6. So the integral is from 6 to 8, but it is undefined at 6, right? It's okay at 8, so we don't worry about it. What we will do then, I will use integral from t to 8, and then push this t approaching 6 to from the right hand side. Okay, so the integral will be limit t goes to 6 from the right hand side, integral from t to 8 of 4 over x minus 6 cubed dx. Okay, and then you do substitution, so on and so forth. I somehow think this will be divergent. I think this will be divergent, but I'm not sure. I am not sure. We can try u equals to x minus 6, so du is dx. Yeah, you do it, I do it too. Integral 6 of 4 u the integral will be 4 u. I think that will be negative 2 to the negative 2 minus limit t goes to 6 from positive side of t minus 6 to the negative. 2. That will be negative 1/2 plus 2 times such limit. means this goes to infinity. So the integral from 6 to 8 of 4 over x minus 6 cubed dx is divergent. I'm about to give you a break, but during your break, I would like you to do a problem, maybe question number 38. Which one you like, number 38 or number 40? Number 38, okay, you do number 38, which is, in case you don't have the textbook, number 38, integral from 0 to 1 of e to the 1 over x over x cubed dx. We have point of singularity, we say, at 0. We have point of singularity at 0. So we have issue at 0. Let me give you like around 6 minutes for this. Together with your break, we come back at 8:40. So this is equal to, let me shift far to the left. Limit t goes to 0 from the positive side. Integral t to 1 of e to the 1 over x over x cubed dx. If my u were 1 over x, if my u is 1 over x, then the u will be negative 1 over x squared dx. You know what? Let me rewrite this first. This is limit t goes to 0 from the positive side. Integral from t to 1, e to the 1 over x. And I want to write this as, this is 1 over x times 1 over x squared dx. Okay. So this then becomes limit t goes to 0 from the right hand side, integral t to, no, actually 1 over t now. That's 1 over t here, while this one 1 over 1 still 1. That's e to the u times negative du. Which is equals to limit t goes to 0 from the positive side. I will absorb the negative here by reversing limits of integrations. Okay, that's integral from 1 to 1 over t u e to the u du. Integration by parts as 1, 0, e to the u, e to the u. So this is limit t goes to 0 from the right hand side of u e to the u minus e to the u from 1 to 1 over t. This will be limit t goes to infinity, t from 0 positive of 1 over t e to the 1 over t minus e to the 1 over t minus when u equals to 1, that's 0. Actually, that's e to the 1 minus e to the 1. Maybe I write it down properly. So we actually now have limit t goes to 0 positive of e to the 1 over t and then 1 over t minus 1. Now, you know what? I don't want to do that. I prefer to do it this way. How to do this? Notice that this goes to infinity. This goes to infinity. This also goes to infinity. That's the problem. Right? So infinity minus infinity, no. You cannot do it directly. You cannot say infinity minus infinity is 0. No.
Factor.
Huh?
Factor.
Factor, okay. So actually I prefer to say, rewrite it as a quotient. So I will make it e to the 1 over t minus t times e to the 1 over t big over t, like that. Maybe like that, I don't know. I think we need to factor, huh? Yeah, you're right, let's factor it. Yeah, the thing is this goes to infinity. This can go to 0, can go to infinity or anything in between, because this goes to 0. This goes to infinity, right? Okay, so I guess, yeah, I will factor e to the 1 over t. I will factor e to the 1 over t, so 1 over t minus 1. How do we argue from here? This is not in definite form though. This is not undetermined, because you will see this goes to infinity, this goes to infinity, right? This also goes to infinity. You see? So infinity times infinity is not undetermined. So this will be, oops, that's actually divergent to infinity. Notice that it is not true if the 0 is approaching, t is approaching 0 from the left-hand side. Why can't you just automatically say it's divergent? Or what is divergent? What do you mean by automatically, first of all? Yeah, what do you mean by automatically there? After I get this, after I get this, after I get this here. No, I cannot though, because if you plug in 0 here, 0 positive, this will be infinity. This one also infinity. Infinity minus infinity is unknown. Yeah, you may have a smaller infinity minus a larger infinity. The difference will be not so large, negative infinity anymore. Right? The thing is, we don't know which infinity is larger. Okay? Yeah, that's the thing. We don't know which infinity is larger. So what you mean by automatic there is actually not automatic, because I can find out this limit here. Take a look. Okay, what is limit t goes to infinity of x t minus t? When you plug in t goes to infinity, this is infinity. This one also infinity. So infinity minus infinity is? You want to say that's 0? Then let me change that t, the first t, into t squared. This goes to infinity. This goes to infinity. Does it mean this is equals to 0? No. So what is infinity minus infinity? Depends on my mood. No, we can't argue that way. We can't argue that way. Okay, so in other words, good thing that you asked me that question. Why can't we automatically say that from here? Why can't we automatically say that from here? Because when you plug in t equals to 0 positive, you'll get infinity here minus infinity, and we know that's undetermined from 6.8 when we did L'Hopital rule. Okay, so the answer is no. Once you get infinity somewhere, then the integral becomes divergent. That's if part of the integral is, but I was not referring to a single limit. I was talking about if you have limit, I'm sorry, integral of something plus integral of something, and one of them does not exist. Then you say that the whole integral is divergent. Okay, but simply because this integral here consists of infinity minus infinity, now you cannot do that yet. They are still under condition of limit. They are under condition of limit. The thing is, can you kill that before you plug in the t equals to 0, or when t goes to infinity in other case? Okay, so looking back to this. Looking back to this, we know that limit t goes to infinity of t minus t. How do you answer this? How do you work this out? You cannot plug in infinity first and then subtract them, right? The correct way is actually t minus 3, t minus t is 0. Even when t is not reaching infinity yet, then this is equals to 0. Now, how about doing this? T goes to infinity of t squared minus t. You can use far end behavior you learn from pre-calculus, but another way to look at that, this is you factor the t, this is t minus 1. Okay, then you will see this guy goes to infinity, this guy goes to infinity also. So infinity times infinity is infinity. That's the correct way. So you can, but you cannot plug in infinity first and then you subtract them. Okay, adding to infinity, yes, will be infinity. Infinity times infinity, yes, will be infinity. But infinity divided by infinity is not infinity, it's not 1. It can be anything in between. Okay, so you need to look back to your 6.8. Look back to your 6.8. Under what situation we call that undetermined. Okay, we call that undetermined if you have 0 over 0, plus minus infinity over infinity, 0 to the infinity, 1 to the infinity, is it right? 0 to the 0. Okay, and then I think it is 1 to the infinity. Maybe infinity to the 1 also. I forgot which case. Let me take a look. Infinity to the 0. Oh, 0 to the infinity is not one of them. This one is not. Okay, and then of course the other one is infinity minus infinity. That's another indeterminate form. Okay, and don't forget that's the reason we learn L'Hopital rule, to know under what situation you cannot just plug in infinity, subtract by infinity. That's a big no, 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 no. Okay, indeterminate. Yeah, that's for number 38. So this one is divergent to infinity. How about number 40? Oh, let's see, I have a chat. Can we do another one with trick? You choose the problem. I don't know which one. The one with trick. Number 36 maybe. Integral from pi over 2 to pi of cosecant x dx. The cosecant is 1 over sine. Right? It's 1 over sine. So it is undefined at from pi over 2. Sine pi over 2 is 1. Sine pi is 0. So it is undefined here. So this will be limit t goes to pi from the left hand side, integral pi over 2 to t of cosecant x dx. That is limit t goes to pi from the left hand side. I wonder what is the integral of cosecant. I think that's natural log of cosecant x minus cotangent x from pi over 2 to t. And then what next? Just plug in t, right? Yeah, let me make sure first. I don't want to make a miscomputation on that further later on. What is integral of cosecant? Yeah, that's right. And this is equals to limit t goes to pi from left hand side of natural log of cosecant t minus cotangent t minus natural log of cosecant pi over 2 minus cotangent pi over 2. I will take care of this later. Minus ln cosecant pi over 2 is 1, cotangent pi over 2 is 0. Now, on the first terms that has the limit condition, that is cosecant, that's 1 minus cosine t over sine t. While this one is natural log of 1, which is 0. Right? And then this is natural log of absolute limit t goes to pi from left hand side of 1 minus cosine t over sine t. Yeah, from there I think I will do L'Hopital rule. Yeah, because it gives me 0 over 0. Right, so I apply L'Hopital rule. So limit t goes to pi from the left hand side of sine t over cosine t. That's tangent. So this will approach tangent from the negative or from the positive side. It will approach 0 from the negative side. Right? But with absolute, it will approach 0. Maybe I write it this way. Okay, that's for another trigonometric part. So your trigonometry has to be stronger. Your trigonometry has to be strong. Okay, so that's basically it for these improper integrals. And then I will go on with comparison theorem. Comparison theorem. I thought ln of 0 is indeterminate. No, that's from, well, when you approach 0 from the negative, that's negative. It is true. But when you have absolute, this is approaching 0 from the positive side. Right? And natural log looks like this. So when you approach that from the right-hand side, that's going to negative infinity. So the absolute value is crucial. Okay, without the absolute value, it will be undefined. Not even indeterminate. No, it's undefined. Okay. So we have to say it's divergent also. Once you say that it goes to negative infinity, then it is divergent. In fact, I think that's the reason you keep on asking that question. So is it divergent or not? Okay. Divergent has two types. Divergent, the following is called divergent. If the limit goes to is infinity, or the limit is going to negative infinity, or the limit does not exist. In these three cases, they are divergent. In these three cases, they are divergent. Okay, so when you ask me, so Thomas, is it divergent or not? I'm not only answering you that it is divergent, I can even get more specific. Is it infinity, or is it negative infinity, or is it does not exist? Okay, let me go back and ask you this question, calculus 1. Calculus 1. So if your teacher teach you other than this, you really have to go back to a calculus 1, drop this class, go back to your calculus 1, get another teacher, because something wrong with your teacher if your teacher didn't just say it this way. When I ask you, when your teacher asks you x goes to infinity of x squared, what's your answer? Does not exist or infinity? Infinity, right? Okay, but does the limit exist? Does the limit exist? The limit does not exist. Okay, but the correct answer is supposed to be infinity. The limit does not exist because it goes to infinity. Okay, so some people, they don't want to think hard. They say this is does not exist, and some teachers just let it go. So it's infinity, therefore does not exist. No, it's not supposed to. The limit does not exist in sense that it goes to infinity. Okay. So this answer is actually more specific than just this. Limit x going to infinity of cosine x, for example, this does not exist. Does it go to infinity? No, it's not going to infinity. In fact, cosine x is always bounded between -1 to 1. The problem is, since your x does not stop anywhere, then your cosine x is oscillating between -1 and 1 indefinitely far. Now, then from here, we say does not exist. Therefore, it is divergent, but not in sense of infinity or negative infinity. Okay? So going back to your question, so is it divergent, Thomas? When I see this, is it divergent? I answer more than just is it divergent or not. I even tell you it is divergent to negative infinity. It's like somebody asked me, Thomas, do you have any kids? I say, I have 2. Not only I answer yes, I even tell you I have 2. Okay, I was being more specific when I say that. Of course, you don't ask me that question, Thomas, are you married? Should I say twice? Right, not only that I answer yes, but I also answer how many times, right? Okay. So the answer, yeah, this kind of answer is more specific than just answering is it divergent or not. Okay. Yeah, so implicitly when you see, oh, the limit is negative infinity, then it must be divergent. Now, comparison theorem at first is hard to understand because we do need to have a lot of experience here. We need to have experience here, but I'll give you the idea. It is as the following. You know what? Before I do comparison theorem, I think I need to do this thing first. Yeah, I think I need to do this one first. Hold on. Something very important later on. This one, the P integral. Integral from 1 to infinity 1 over x to the P dx. When will this be convergent? When will this be divergent? Now we will start with when P equals to 1. For P equals to 1, maybe I do the limit first. So this is limit t goes to infinity, integral from 1 to t, 1 over x to the p dx. When p equals to 1, that integral is limit t goes to infinity of 1 integral from 1 to t of 1 over x dx. This is limit t goes to infinity of ln absolute of x from 1 to t, which is limit t goes to infinity of ln t, because t is positive, minus ln 1, which is 0. You can see this actually diverge to infinity. What happened when p is greater than 1? For p greater than 1, then that integral becomes limit t goes to infinity of, I'm talking about this integral here. This one. Okay, I'm talking about that one. That will be 1 over 1 minus p x to the 1 minus p from 1 to t. But if p is greater than 1, So 1 minus p will be, so 1 minus p will be negative, right? 1 minus p will be negative. Agree? So this will be limit p goes to infinity. Let me take the 1 over p outside. One over 1 minus p outside, limit t goes to infinity of t to the power of 1 minus p minus 1. But the thing is, as we have seen here, that this is negative, this is negative, then you end up with infinity to the power of negative exponent. Infinity to the negative exponent is equals to 1 over infinity to the positive exponent. That's 0, right? Okay, so that is equal to 1 over 1 minus p times 0 minus 1. That's 1 over p minus 1. So it is convergent when p is greater than 1. Now notice that when p is less than 1, then we will end up with 1 over 1 minus p, limit p goes to infinity of t to the 1 minus p minus 1. If p is less than 1 means 1 minus p is positive. 1 minus p is positive. And then this will go to infinity instead. Summary. The p integral from 1 to infinity of 1 over x to the p dx is equal to 1 over p minus 1 for p greater than 1, divergent for p less than equals to 1. Let's try to imagine. I wonder if there's a way for me to graph that. Nice. So let's say for example, integral from 1 to infinity of 1 over x squared dx. Now notice the p here is 2, right? The p is 2. That's p integral p equals to 2, which is greater than 1. Right? So this is equals to 1 over 2 minus 1, that's equals to 1. That's convergent. We can even tell the integral. Okay. How about when I have integral from 1 to infinity of 1 over x to the power of 1/2 square root of x dx. then this is still P integral by our definition. P integral is the integral of 1 over x to the p with the limit of integration from 1 to infinity. From 1 to infinity. 1 to infinity. Okay, that's what we call P integral. Now here, the P is 1/2, which is less than 1. So this is divergent. In fact, we can say this goes to infinity. Not only divergent, it's divergent to infinity. Okay, comparison theorem. Comparison theorem has a simple basic idea, but in application, it takes a lot of practice, And there's a chance, I have seen that a couple of times, I found students did the problem better than me. Now, let's see. What is comparison theorem? It says the following: let fx greater equals to gx greater equals to 0. So both these functions are non-negative, okay, on interval a to infinity. I think I need to say that f and g are continuous. So imagine the graph as the following. So let me use fg to be the greater function. F function is greater, and then the g is less than that. Oops. Smaller. Okay, this is my gx. This is my fx. Starting from a, now, first one. If integral from a to infinity of fx dx is convergent, then integral from a to infinity of gx dx is also convergent. Basically, if a function gx in this case is bounded above by a function whose integral is finite, therefore it's convergent, right? If the area under this fx is finite, then the area under gx should also be finite, right? Okay, try to make sense of that. So to show that this kind of integral from a certain number to infinity is convergent, what you can do is you bound it, find another function greater than that, but is convergent. Second, if the integral of the smaller function is divergent, can you tell divergent to what? Is it divergent to negative infinity or does not exist? Or positive infinity? Instinct, please. When we say divergent here, in what sense it will be divergent given the situation? Is it divergent to infinity, does not exist, or divergent to negative infinity? All of the above. No, it's not. It will be divergent to positive infinity. Cannot be divergent to negative infinity. Why not? This function is positive, non-negative function, so the area under the curve cannot be negative. Right? Okay, that's one. And if you think about that, the area up to certain place, right, for non-negative function, when you increase that, then the limit will increase. It will not go to negative. No. You keep on adding a positive area, keep on adding positive area, right? So if you can only add positive area, it will not become negative. And when we say does not exist, it refers to the case that when you go, it's oscillating plus minus plus or oscillating 1, 2, 1, 2, 1, 2, for example. But it's impossible. You are keep on adding a positive number. And if you keep on adding a positive number, the area can only increase. Okay, the area can only increase. Now, if it can only increase, either it increased to a certain number, therefore it's convergent, or if it is divergent, that can only divergent to infinity. But here you need to have some instinct though. Here you need to have some instinct. Now, if you have positive number plus positive number plus positive number, you keep on adding positive area. And you say at the end, oh, you know what? The area is divergent. And will the divergent refers to negative infinity? No way. You are adding positive numbers. Cannot be negative. Right? Can that be does not exist? No, it won't. Does not exist if it oscillates. If it oscillates. But you have oscillates if you have plus minus like that. Okay? Now, what this theorem says is, if the lower function convergent is divergent, the area of the smaller function is divergent, then the area on the larger function, larger integrand, will also be divergent. Does the converse of the theorem work as well? No. No, it doesn't work the other way around. No. Let's do some problems first to have a better instinct on this. And then I will show you the cases where the converse doesn't work. Okay? So let's understand this comparison theorem first well. Okay, I pick questions from our textbook. For example, I think number 8 is good. Number 8. Integral from 1 to infinity of 1 over 2x plus 1 cubed. dx. Notice that 1 over 2x plus 1 is less than 1 over x on the interval 1 to infinity. You see, right? Therefore, when you cube that, one over x cubed still greater. Are you with me? So this is less than equals to integral from 1 to infinity of 1 over x cubed dx. And we know this is convergent. In fact, we can say this is 1 over 3 minus 1. Right? So, integral from 1 to infinity of 1 over 2x plus 1 cubed dx is convergent. If your question only to answer is it convergent or not, then we are done. Right? And I believe we did this number 8 earlier. Let's see, what's that? I believe I did number 8. Yeah, we did number 8. In fact, we get that's 1 over 36. Right? Okay, that's what our textbook wants though. If it is convergent, then show it converges to what, right? Okay, now, but if you just want to answer is it convergent or not, this is actually good enough. You're bounded above by something convergent. Okay, bounded above by something convergent. Number 50. Number 50. Use comparison theorem to determine whether the integral is convergent or divergent. Integral from 1 to infinity of 2 plus e to the negative x over x. Is this convergent or divergent? Now try, have some instinct first. Have some instinct first. Do you think this will be convergent or divergent? And then you do the bounding. Now, what happened here, we can say, notice that this guy here is definitely greater than 2. Is it right? Is that right? But at the same time, this is 2 times integral from 1 to infinity of 1 over x dx. Since integral from 1 to infinity of 1 over x dx is a p integral p equals to 1, then this integral 1 to infinity of 1 over x dx is divergent. So this guy here is divergent, but this guy is smaller than this. If this is divergent to infinity, then this must be divergent to even larger infinity. What is larger than infinity? Wow, that's a philosophical question, huh? What is larger than infinity? Infinity plus some positive number. Okay, so by comparison theorem, integral from 1 to infinity of 2 plus e to the negative x over x dx is divergent. In fact, we can say it's divergent to infinity. Like what I said earlier, this part here, they don't give us a lot of problems, but it's nice to explore this. Let's see number 52. They definitely don't give us enough problems though. Number 52, integral from 0 to infinity of arctan of x over 2 plus e to the x dx. How to do this problem? It's kind of like interesting to see how we massage this. This is less than equals to integral from 0 to infinity of arc tangent of x over e to the x. Is it right? Dx. If you divide by a smaller positive number, then the quotient should be larger. Okay, that's because 1 over 2 plus e to the x is less than 1 over e to the x. Yeah, the reason is the reciprocal is true. And they are positive. Okay, so that's what I use here. If you divide by a smaller positive number, then you get a larger quotient. Second thing that I will do is arctangent arctangent or tangent inverse of x is actually between negative pi over 2 to pi over 2 in general. Okay, but on intervals 0 to infinity, tangent inverse x is from 0 to pi over 2. So it is positive. It's non-negative, okay, bounded above. So I can say now that this guy is less than equal to integral from 0 to infinity of pi over 2 over e to the x dx. Which is pi over 2 limit t goes to infinity from 0 to t e to the negative x dx. Now then what you need to do is to show that this integral is convergent. This limit is convergent. That's pi over 2 limit t goes to infinity of negative e to the negative x from 0 to t. So that's pi over 2, 1 minus limit t goes to infinity of e to the negative t. That's pi over 2. Okay, because it's bounded by something finite, then the integral that we have earlier, integral from 0 to infinity of arctangent of x over 1 plus e to the x, actually 2 plus dx is convergent. Last one, number 54. I really thought in 2.5 hours I can finish this section, apparently no. Number 54, integral from 0 to pi of sine squared x over square root of x dx. How to do this problem? Trig sub? No, you already have trig. You don't want to do trig sub. No, you don't have to compute this though. No, you don't have to compute this. You don't have to compute this. Do comparison. That's what I say. They don't ask you to compute what's the answer. They only ask you, is it convergent or divergent? That's all they ask. Okay, that's all they ask. So then, can you find out a way? Can you find out a way such that should I bound it above or should I bound it below? Okay, let's do some guessing game. So let's see. I know that sine x is between -1 to 1, so sine squared x is between 0 to 1. Right? For every x. For every x. Okay? So I can say this is less than equals to integral from 0 to pi of 1 over square root of x dx. Is it a p integral? Is this a p integral? No, it's not. Why it's not? The limit of integration is not from 1 to infinity. So we cannot call that p integral. Okay, you can say that's p integral in different form. Okay, you can say that's p integral in different form, but let's just compute this in full then. So instead of computing this, I compute something greater and want to show that this is convergent. Okay, so if I can bound it above by a convergent integral, then the lower integral will be the integral of the smaller function must be convergent. Okay, so let me just compute this thing. This is equal to limit t goes to 0 from the right hand side integral t to pi of x to the power of -1/2 dx. This is limit t goes to 0 positive of 2 times x to the power of 1/2 from t to pi. This is 2 times square root of pi minus square root of, oh, sorry, limit. Don't forget the limit times. Limit t goes to 0 positive of t to the power of 1/2. But that's 0 there. So the answer here is 2 square root of pi. Okay, notice that you you bound it above by a convergent function, a convergent integral. Zero to pi of sine squared x over square root of x dx is convergent. Now let me answer that question. Is the converse is true? The answer is no. The answer is no. Like if the integral of the smaller function is convergent, now it is possible that the larger function actually goes really, really big. So no. It has to follow this. It has to follow this. Okay. For the lower function to be convergent, it has to be bounded above by a convergent integral. Likewise, for the bigger integral to be divergent, the bigger function fx in this case is the integral of fx to be divergent, then you need to start with a smaller function, but the integral of that smaller function is divergent. Therefore, the bigger one must be divergent. Okay, but we cannot go the other way around. Simply because I'm smaller than you and I'm finite doesn't mean you must be finite. No, because I'm not the one bounding you. You're the one bounding me. So you can be still infinity and I'm still finite. Okay. I want to erase this. Okay, your suggested homework. In fact, I want to specifically say I need you to do. I need you to do from this section. Suggested homework from this 7.8. I need you to do number 5 to number 39 to the odd ones. And then continue number 49 to number 59. 49 to number 59, do the odd one also. I specifically want you to do number 57, 58, 59. This type of problem shows up a lot, not only in math, but also in engineering. If you have a chance, think about number 61. That's basically what I said earlier. Okay, I think that's all for today. See you then on Wednesday.